Lattice problem. Shortest vector problem SVP. Hardness results. The exact version of the problem is only known to be in p-hard for randomized reductions. By contrast, the corresponding problem with respect to the uniform norm is known to be in p-hard. Algorithms for the Euclidean norm. Gap SVP, SVP. Closest vector problem CVP. Relationship with SVP. Hardness results. Sphere decoding. Algorithms for CVP, especially the Fink and Post variant, have been used for data detection in multiple input, multiple output MIMO wireless communication systems for coded and uncoded signals. In this context, it is called sphere decoding due to the radius used internal to many CVP solutions. It has been applied in the field of the integer ambiguity resolution of carrier phase GNSS GPS. It is called lambda method in that field. In the same field, the general CVP problem is referred to as integer least squares. Gap CVP. Known results. Shortest independent vectors problem SIVP. Bounded distance decoding. Covering radius problem. Given a basis for the lattice, the algorithm must find the largest distance, or in some versions, its approximation from any vector to the lattice. Shortest basis problem. Use in cryptography. Average case hardness of problems forms a basis for proofs of security for most cryptographic schemes. However, experimental evidence suggests that most NP-hard problems lack this property. They are probably only worst-case hard. Many lattice problems have been conjectured or proven to be average-case hard, making them an attractive class of problems to base cryptographic schemes on. Moreover, worst-case hardness of some lattice problems have been used to create secure cryptographic schemes. The use of worst-case hardness in such schemes makes them among the very few schemes that are very likely secure even against quantum computers. The above lattice problems are easy to solve if the algorithm is provided with a good basis. Lattice reduction algorithms aim, given a basis for a lattice, to output a new basis consisting of relatively short, nearly orthogonal vectors. The Lenstra-Lenstra-Lovász lattice basis reduction algorithm LLL was an early efficient algorithm for this problem, which could output an almost reduced lattice basis in polynomial time. This algorithm and its further refinements were used to break several cryptographic schemes, establishing its status as a very important tool in cryptanalysis. The success of LLL on experimental data led to a belief that lattice reduction might be an easy problem in practice. However, this belief was challenged when in the late 1990s, several new results on the hardness of lattice problems were obtained, starting with the result of Ajtai. In his seminal papers, Ajtai showed that the SVP problem was NP-hard and discovered some connections between the worst-case complexity and average-case complexity of some lattice problems. Building on these results, Ajtai and Dwork created a public key cryptosystem whose security could be proven using only the worst-case hardness of a certain version of SVP, thus making it the first result to have used worst-case hardness to create secure systems.